Today we're going to be talking about exponential functions. Exponential functions are functions that increase rapidly, unless they're exponential decay functions, in which case they decrease rapidly. But today we're only going to talk about exponential growth. So think about the question, and you've probably been posed this question before. What if I gave you 1 cent on day one, and then 2 cents on day two, and then 4 cents on day three, and each day I gave you twice as many cents as I gave you the last time? Well, let's think about what this would start to look like. So after the day where I gave you 4 cents, it would be 8 cents, then 16 cents, then 32 cents, 64 cents, and then $1.28. So now we're looking at dollars. The next day it would be $2.56. The day after that it would be $5.12. And then the day after that it would be like $10 and some cents. So this is an exponential function that started off with very little, 1 cent, and after about 10 or 14 days, we're talking about more than $10, and then 20, and then 40, and then 60. So this is an increasing function. So whenever you multiply something successively by a positive number greater than 0, it will increase very quickly. We're going to look at a graphical representation of a function that increases very quickly. Let's look at this here. We're going to look at this animation real quick. This is something called a Sierpinski triangle. Okay, right now at iteration 0, we have one triangle. What we're going to do is we're going to connect within this blue triangle these 3 dots, and we're going to cut that out. Okay, so we cut out the middle, and now we have 1, 2, 3 blue triangles, and this is after one iteration. So we started with 1, we multiplied that by 3 and got 3. So if we multiply that by 3, we will get 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so after 3 iterations, how many blue triangles will there be? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 3, well, 27. So we took the last number and we multiplied it by 3 again. Okay, so how many are here? Well, whatever 27 times 3 is. Okay, here they're saying that the Sierpinski triangle is an example of a fractal. Fractals are interesting. This is not an interesting fractal. Okay. So, here we see, well, to get the number, we just exponentiate 3 to the number of times we've walked through this process. So for 0 iterations, just starting out, 3 to the 0. Well, as you know, any number to the 0th power is 1. It doesn't matter what it is. Okay, so for instance, negative 1 to the 0th power is 1, interestingly enough. Let's go over some more examples. 40 to the 0th power, hey, it's 1. 0.0001 to the 0th power, hey, it's 1. Okay, so on on the 0th iteration, we have one upward triangle. 3 to the first power is 3, because any number exponentiated to the first power is just that number. 3 squared, or 3 times 3, is 9. 3 cubed, 3 to the third power, it's 3 times 3 times 3, which is 27. Okay, we start doing all this arithmetic. We get 3 to the fourth power is 81. Okay, the next one is going to be 243. Now what we want is we want to say, hey, what is this for any old number? So we'll use the integer number n. What is it going to be? It's going to be 3 to the n. And this works for any number of iterations. So here's our function. We could also write this like this. Oops. Let's see here. 3 to the n. Well, we can put this in function notation. We can say f of n equals 3 to the n. Well, if we don't want to limit ourselves to integers, we could say f of x is 3 to the x. So now this looks a little more familiar to us. Okay, what's this going to look like when we graph it? Well, here they're noting that we only have integer values of n for this problem. There's no such thing as a half an iteration for this case. In general, scientists and mathematicians will allow any number of iterations, or any number as the argument of the function. But for this case, we only have integers. Let's look at what this function looks like. Okay, if we graph this function, here we have x is 0, and we get 1. Okay, so we start off away from the origin by 1. When x is 1, we got 3. Well, you can see when we graph this, it's increasing really quickly. So, yesterday we were looking at inverses of linear functions, and today we're going to think about, well, what would the inverse of 3 to the x look like? Well, if you remember that you can reflect it across y equals x, you know that it's going to be along here. And while this one increases rapidly, this one is going to increase slowly. Now, if you remember from yesterday, we can get this inverse function by flipping the axes, by making the dependent variable the independent variable and vice versa, by taking what's on the y-axis and putting it on the x-axis, and by taking what's on the x-axis and putting it on the y-axis. Okay, so you can see that these are symmetric about y equals x, which would go right along the middle of these. So here they're leaving this as a question mark. What is this function called? We're going to learn that right now. Okay, this is called the logarithm. The logarithm is the inverse of the exponential function. We're going to talk really quickly about what is a log. On the wall, you'll see a poster that asserts the following. It says something like this. If we have an exponential base b, if b to the x equals y, then we have an equivalent statement. If this is true, then this is also true. Okay, if you have b to the x equals y, well then log base b of y equals x. These are inverses. Let's look at a better graph of these two functions. This graph we were looking at is sort of feeble here. Okay. So here the red function is y equals 3 to the x. You can see it's increasing rapidly. Here we've got y equals log base 3 of x. It's increasing slowly. And you can see these are symmetric about y equals x. The domain of y equals 3 to the x is all all numbers. This is defined across all numbers. The range is all positive numbers. So the range is everything above the x-axis. Now for the inverse, the range is all real numbers. This goes off towards infinity very slowly, and this goes down to negative infinity very quickly. But the domain is all positive numbers. So this is an important finding, that the domain of a function is the same as the range of its inverse. And that's written up on the front of the classroom. And this is a complicated idea. You can always see it graphically if you have the right domain restrictions. The big takeaway from today is we've really learned what a log function is, what the logarithm is. Now, most mathematicians use log with a constant base for different applications. Usually it's a special number called e, which is called the base of the natural log. Scientists sometimes use 10 as the base of the log, especially chemists. So, but in general, you can define a log with a variable base, depending on what you're starting with. Now, in the case of the Sierpinski triangle, the base was 3. You kept multiplying by 3. With the example we started class with, what was the base? It was 2. We kept multiplying the previous money by 2. So that would be f of x equals 2 to the x. Okay, so we're going to be exploring log functions more. We also need to learn how to deal with these algebraically. And we've got a pretty good conceptual base for what a log is. We're also going to be working in class on how to do the algebra with a log. Okay? You should be able to do student activity sheet 3 or whatever you have at your desk.